Hi, everyone, and welcome to our new chapter. We're starting chemical reactions today. It's a fun chapter to do. We'll have a lot of little video clips so you can see some reactions in action, and we'll learn how to write them and balance them and identify them. So let's jump right in for today. Our objectives for today are to decide or identify what the signs are of a chemical reaction, and then also we're going to take a look at how we write equations based on sentences or word equations. So let's jump right in. How do we know a chemical reaction has occurred? Well, the easiest way would be if we could see the atoms, right? So if we can get down at the molecular level and actually see the atoms, we could easily see if a chemical reaction has occurred. But we usually can't. So let's talk a little bit first about what are some of the things that are happening in a chemical reaction. What are atoms doing? Atoms blank with other atoms to form compounds. Atoms bond, right, with other atoms to form compounds. What kinds of compounds can we have? Right, ionic and covalent. Those aren't the only two, but those are the ones we like to deal with. A blank blank occurs when atoms and compounds are rearranged. That is the main idea of what we're talking about here. Reaction. Chemical reaction occurs. Okay, and lastly, chemical reactions, some bonds are blank and new bonds form. Some bonds are broken and some new bonds are formed. So that's the basic idea of what we have here. So when we want to look at a chemical reaction, we're looking for certain signs that a reaction has taken place. So here are some of those signs. Let's see if you can identify them. Here's the first one. Okay, so what sign was shown there as a sign of a chemical reaction? That's right, it was a color change, right? So that was a rainbow reaction, pretty cool. It goes from the dark purple all the way up to this light, like a rusty orange color. You can see there. Okay, how about in this one?
All right, what we have here are two beakers, each containing dissolved aqueous ionic compound. In the beaker on the left, we've got magnesium sulfate, and you can see that that is a clear and colorless solution. Looks just like water on first glance. And over on the right, we've got sodium hydroxide, which is also clear and colorless. Again, looks just like water. And what we're going to do here is we're going to mix these two and see what happens. You can see
Okay, and what we can see here is that the two clear, colorless solutions mixed together form a cloudy solution. And what do we call that? That is a precipitate, right? Precipitate. Okay, and a precipitate is a solid, right? It's a solid that forms when we mix two solutions together. So if we were to let these this new mixture or new compounds sit here, those cloudiness, that the particles that are making that solution cloudy would eventually precipitate or fall down to the bottom, and we get a little layer of a white powder at the bottom of the beaker, with the rest of the solution essentially being clear. Okay, okay, and this one you're going to see two signs of a chemical reaction, so look for two signs. Okay, so did we catch that one? Let's say that was both bubbles forming, right? And there was a temperature change, which indicates that there was a change in energy. So those are our four main ways we can tell there's a chemical reaction occurring. If there is a color change, if we have the formation of a precipitate, if the gas forms, which means bubbles or fizzing, and a change in energy, which could mean either a increase in heat or a decrease in heat, or a light energy being given off. There's also a fifth one that's a little less reliable, and that would be the presence of an odor. So obviously I can't demonstrate that one as much to you in video, but that would also be another indication of a chemical change occurring. Okay, so again, we might not always see one of these five signs of chemical change. We would have to look at things at the molecular level in some instances in order to actually see that a reaction has occurred. And we don't generally deal with reactions that require that level. Most of the time, the reactions that we deal with on an everyday basis display one of those 4 or 5 indicators of a chemical reaction occurring. Okay, so I'm going to give you some practice. Which of these is a chemical reaction? Ice melting, forming hydrogen and oxygen from water, iron rusting, and bubbles forming when we open up a can of soda. Okay, and yes, so ice melting. Ice melting is solid water that becomes liquid water. Right? So that is not a chemical reaction. That is something that we call a phase change. It changes from the solid phase to the liquid phase, but not a chemical reaction. Now, however, the second one, we actually are changing the water, right? We're breaking the water up into its hydrogen and its oxygen. So we're breaking bonds in this one. And so, yes, the formation of hydrogen and oxygen from water is a chemical reaction. Iron rusting. Iron rusting is also a chemical reaction. It's the reaction of iron with oxygen to form iron oxide, which has definitely a different color, right? It forms a very unique rust color we're used to. And bubbles that form when we open a can of soda, that would not be a chemical change. Again, that would be a phase change. Usually those bubbles are carbon dioxide, and they are dissolved into the liquid at high pressure. So when we release that pressure by opening the soda can, the gas is allowed to escape. But it's not a chemical reaction that's taking place. The gas was always there to begin with. It just needed to be released. Okay, so let's look at it at the molecular level. Do you think this represents a chemical reaction? Okay, and the answer is no, right? Because we are not breaking any bonds. We have some carbon dioxides here, and it doesn't matter if you recognize that as carbon dioxide. We could see it's a black and 2 reds being bonded together, and we still have a black and 2 reds being bonded together. So this would be another instance of a phase change, right? So in the reactants on the left-hand side here, these are tightly packed together. This is perhaps the solid or the liquid phase. And on the right-hand side, it looks like the molecules are spread out, they're moving fast. We've got little, blurs of movement. So those are probably in the gas phase, right? So we have just a phase change here and not a chemical reaction. How about this one? Okay, so this one is a chemical reaction because we start with something that's called a hydrocarbon. There's an oxygen in there, we just can't see it in color. And we end up with 2 new compounds, which happen to be water and carbon dioxide. So we break some bonds and we form some new bonds, and so we definitely have a chemical reaction. How about this one? Well, yep, this is the one that we saw before, right? So this is the breaking down of water into the hydrogens, and oxygens that it's made up of. So we break bonds, right? We break these bonds here, and we form new bonds on the product side. So yes, this is an example of a chemical reaction. So how do we express these chemical reactions? Well, we use equations. Equations are something that can be universally understood. So scientists in any country of the world will use the same symbols for the elements, even if they say the names differently. They use the same symbols for the elements, and they express things in the same way, just like we do in math, right? So that everybody can understand it. So chemical equations are trying to represent what's happening at the atomic or molecular level. So this is an example of a reaction. In this case, it happens to be methane. Methane is a hydrocarbon, an organic compound. We don't talk about organic compounds too much, but it's methane, and it's reacting with oxygen, and it's going to form carbon dioxide and water. So this is what it would look like at the atomic level, and this is how we would express it as a chemical equation. So methane is CH4, it's a gas. It reacts with oxygen, which is a gas, forms carbon dioxide, which is a gas, and also water. And because this reaction produces a lot of energy, the water is also in the gaseous state in this reaction because it's so hot that it gets vaporized. Okay, so let's see here. What are some of the things that we saw in that chemical equation? Well, one of them is the state of matter. We like to indicate what the state of matter is for each of our substances in the reaction. And you've seen this before in previous labs, right? So we have gases, liquids, solids, and aqueous solutions. And again, an aqueous solution is anything that we dissolve in water. So it could be an ionic compound, could be a covalent compound, but it's been dissolved in water. So it becomes an aqueous solution. The water itself is not a part of the reaction. If the water itself was part of the reaction, we would write that separately. So when we have something that's an aqueous solution, we know that the water is just there as a medium for the reaction to take place, and is not actually taking part in the reaction itself. Okay, here's some other equations that we will see often in chemical reactions. So remember, first of all, that we are always starting with reactants, and they are becoming products. Okay, reactants become products. So that arrow means uh, forms, technically produces, or yields, right? Any of those words may be used for the arrow. Now, if we see a double-headed arrow, this is an indication that this is a reversible reaction. This is something that hopefully we'll get to at the end of the year. Some reactions can be reversed. Some chemical reactions can be reversed. So a lot of times when we're like in, early like middle school and things like that, we talk about the difference between a physical change and a chemical change. One of the things we say that distinguishes the two is that chemical changes are not reversible. Something like burning wood or cooking an egg, you can't go back to the wood, you can't go back to the raw egg. And in a lot of cases, that is true for chemical reactions. But we do have some reactions that are reversible. They can go back and forth between being reactants to products to reactants to products. So if we have that kind of reaction, we use a double-headed arrow to show that. Okay, we have the plus sign, which means the same thing it does in math, right? It means that our substances are reacting, reacts with, or simply is, exactly what it says, in addition to, right? The add side, in addition to, is on the product side. So this would be on the reactant side. It would say it would be reacts with or is added to, and then this would be what it would mean on the product side, right? Which means we have something in addition to plus something else. Okay, we've got the arrow with the delta over it. So the arrow with the delta over it means that heat is added to this reaction in order to make it go. And similarly, we have the arrow with the compound over it, and that compound would be a catalyst. So that means that a catalyst is required to make the reaction go. Now on this side, we've got two. We've got the up arrow and the down arrow. So the up arrow indicates that gas is formed, but we're not really going to use that. We're just going to use the G to show that. And the down arrow would indicate that a precipitate is formed. But again, we're not going to use that. We're just going to use the S. So we are not going to really use these too much. But again, they are possible. You could see them in websites and things like that to indicate a gas or a precipitate. All right, there's one other thing we need to know before we can get started writing the equations, and that is diatomic elements. Diatomic elements, let's see, what does their name indicate? So diatomic, di meaning two, right? Get my pen, there we go. Di meaning two, and atomic, so two atoms, right? So these are elements that exist in nature as two. They come in pairs. They are molecules. And there's a set of them. There's only 7. This is what they are. So we have hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. So whenever you see hydrogen in a chemical reaction, you are going to need to know that you have to write H2 and not just H. If you see oxygen, you're going to need to know that you have to write O2 and not just O. Right? So all of these elements always exist as twos, as diatomic molecules. And there is a way to remember this. There's many ways to remember this, but this one seems to be the most memorable. Have no fear of ice cold beer, right? So we've got HNFOIC and BR, Cl and Br, right? So we can remember those diatomic molecules relatively easily. Many students have used this phrase in order to remember those. Okay, so let's practice with a couple, right? We have the reaction that happens when we have natural gas, and that natural gas is methane, right? So that's the reaction that we saw before. Methane reacting with oxygen to form carbon dioxide and water. So this is exactly what you're going to get. You're going to get a sentence, and you have to translate that sentence into a chemical equation. So if we recall from before, this is what it looked like. You're not going to have to do this part. You're not going to have to draw the the shapes, but you're going to have to be able to write the equations. Okay, so we have methane, and again, if it's a compound that you wouldn't be familiar with, I would give you the formula for that. So methane is CH4. It's reacting with oxygen. So again, remember, you have to know oxygen is going to be an O2, forming carbon dioxide and water. Okay, so our reaction here, we have two gases resulting in also two gases. And the reason that water is a gas in this reaction is because this produces heat, right? So this is what we use in our stoves and things like that. So the heat is going to vaporize the water. So it's going to be gaseous water instead of liquid water. Okay, let's try another one. Solid sodium reacts with chlorine gas to form solid sodium chloride. So sodium is not one of our diatomic molecules, so we can write it as a single atom, and it is solid, and it's going to react with plus chlorine gas. Now that was one of our diatomic molecules, right? So that's Cl2, also a gas, and it's going to form, arrow, solid sodium chloride. So now here's where we go back and where we're happy we learned this the first time. When we write sodium chloride, we have to consider going from the formula, or I'm sorry, going from the name to the formula. So first off, we have to know what kind of compound is this? Is this ionic or covalent? And it's ionic because it is a metal, right? It's a metal reacting with a non-metal. Okay. So now we have to figure out the charges, right, and balance the charges. So if we have an ionic compound, what you have to remember is you have to balance the charges, right? Whatever that compound is, we have to balance the charges. So sodium is in group 1. That means it's going to form a 1 plus. Chlorine is in group 7. It's going to form a 1 minus. So this one's pretty easy because we have 1 plus and 1 minus. They're already balanced out. We have NaCl. And from the sentence, I know that it's a solid. Now, I want to point something out here. Notice that I told you that chlorine always exists as a diatomic molecule, and that is true when it is by itself, right? By itself. When it is in a compound, however, it can be whatever is required of it. So it doesn't need to be a Cl2. It can be a Cl. It could be a Cl2. It could be a Cl3, whatever the charges require of it. So what the main idea here is that the subscripts do not carry over, right, from the product side to the reactant side. The subscripts have to be determined from the charges or from the name of the compound that it forms as a product. You can't just take the subscripts from the reactant side and transfer them over to the product side. You have to figure out what the products are going to be based on the charges or based on the name if it's a covalent compound. All right, let's try one more. Solutions of magnesium sulfate and sodium hydroxide are reacting to form an aqueous sodium sulfate and a precipitate of magnesium hydroxide. Okay, so before we even start writing, let's get into these formulas here. Okay, so I look up magnesium. It's in group 2 of the periodic table, which means it's going to be a 2+ ion. Sulfate, ATE. Where am I going to find that? Right, in the polyatomic ion sheet. So I look that up, it's SO4 2-. Okay, so when I put those together to form magnesium sulfate, I have to balance the charges. And again, I'm lucky here, nothing fancy, right? It's 2+ and 2-, so they're already balanced. I'm told that it's a solution, so this is aqueous. It's going to react with sodium hydroxide. So sodium, again, is a plus. Hydroxide, hydrogen and oxygen, so that's polyatomic. Look that up, OH, and it has a charge of 1-. So again, this is an easy one to write. 1+ and 1- are going to balance each other out. And again, this is a solution. Okay, they react to form. So here's my arrow. I'm going to the products now. I'm going to get aqueous sodium sulfate. So let's do Na+ and SO4 2-. Now, in order to get this formula, again, I have to balance the charges. So I'm going to need 2 sodiums for every 1 sulfate, right? Because I have Na is a plus, SO4 is a 2-, right? So I'm going to need another sodium in order to have 2 pluses and 2 minuses balance each other out. So Na2SO4, which is going to remain in the solution, and it's going to also produce magnesium hydroxide. So Mg2+, OH-. I have the same situation, right? Except I have a 2+ and a 1-, so I'm going to need another OH- so that my pluses balance out my minuses. All right, so this is going to form magnesium hydroxide is MgOH2, and it says it's a precipitate, which means it's a solid. It's going to fall out of the solution. Okay, so you're putting all your skills to use here, the naming and the formula writing, in order to write the reactions that you have, the equations. Okay, so that's it for today. Tomorrow, you're going to practice this with the assignment. Again, that's tomorrow, not today. You're going to practice this in OneNote. You have an assignment called Writing Chemical Equations, and you have about 15 of these to practice with. So think about tonight if you're not, if you're still a little shaky in the formula writing, going from names to formulas, I would suggest you do a little more practice on that, get yourself up to speed so that you're ready to write the equations tomorrow.